on mechanical systems and control. Before we start with today's lesson, I want us to talk about the assessment I have sent to the SMT assessments, short assessments. And I hope that you are busy writing them and you will, it's just as short, it's like a classwork that I've sent. And I want you to try again and upload it to the drive, the school drive. And as a backup, send it to my email address. I gave you my email address yesterday. I will give you my email address again today before the end of this lesson. I'm typing my email address here. That's my email address. You can send it to me too as backup. Thank you. Let's continue with today's lesson. Here we have some background noise there. It's people on the other side. Right. We are looking at gear systems and their drawings. Okay, and then we are looking at winches too. Remember, we are given a problem to solve. Where we were told to design a winch which would be 3 times powerful than it is right now. It must be able to carry the load of 3 times the average size of, yes, that's my email, Lesedi. Yes. Now, yesterday we started looking at winches, right? Now, a winch is normally a system with gears and pulleys. It is powered where it has a motor. So it can be powered by alternating current or direct current, or it can be driven manually. So what you see there, never mind the labels and the numbers, don't worry about them. Just look at the structure. You see there on number 22, okay? What is labeled 22 there is a crank. So it means for this winch to start working, somebody has to put their hand there and wind the crank so that this cable can be released into the pulley system. Now the movement of the crank will be controlled by the gears there. When we look at the driver gear is small, much smaller than the driven gear. This is the driven gear. How do you know that this is the driver gear? We know that because it is directly connected to the crank. So that is where the input is. So the input is on the axle. This is the axle of the gear. The input is on the axle of the small gear. So that small gear is the driver of the big gear. And I want to see if you understand this gear arrangement. I want to see if you understand it. What is the output here? What output do we get here? Do we get an output of mechanical advantage or an output of a speed advantage? Grade 8. Come, grade 8. Grade 8, I want you to analyze the output of this gear system. We get mechanical advantage because the driver is smaller than the driven gear. But when we look at mechanical systems, okay, this applies even to levers. This applies even to pulleys, where the driver is small and the driven is bigger, what do you get? You get mechanical advantage because input force is multiplied in the bigger output. Even if you can do hydraulics and pneumatics, you will see that where the input, the size of the input is small, the input force is multiplied in the bigger, in the area of the output. Okay? Just put that in your mind and you will know that that is how we acquire mechanical advantage. Okay? The area of the input and the area of the output becomes very important when it comes to mechanical advantage. Input force is multiplied in the output if the area of the output is bigger. If you understand that, you're understanding the basics of mechanical engineering. Okay, now, when you put an input, a small input here on the crank, it is transferred, the force is transferred to the driver. The driver is small and the force is multiplied in the bigger gear, and then we get great output force. And that is what is going to operate this winch. That is what is going to operate this winch so that it can release the cable to the pulley system. Right? Hello, Simone. Welcome to our class. I hope you enjoy it. All right. Now, let us look at this winch. Right. A winch is normally connected to a motor. It is connected to a motor normally. Remember yesterday we looked at this winch and I said there should be a gear system here. Okay. Now I got a clear explanation that this one doesn't have a gear system. A winch is used to lift loads in a mine. The winch consists of an electrical motor and a winch drum on which a cable is wound. There's the winch drum, there's the motor. So this one uses electricity. It is not like this one, which is operated manually. It uses electricity. So that's why we have a motor there, an electric motor. All right. Now, this winch, it can carry 10 tons of load. Okay? 10 tons of load. Okay? If the motor is connected directly to the winch drum without a gear, the winch can lift a maximum of 2,000 kilograms. Okay, like this one, without a gear system. The capacity is 2,000 kilograms that it can carry. It can lift a load of 2,000 kilograms. So I want you to understand the principle of a winch, okay? So what you don't see on this winch is this part. So a winch will be operated from here to get an input on this system. That's why I said when you wind this crank, you release the cable to a gear system, to a pulley system. This is the pulley system that I was talking about. It can be one or a number of pulleys that make up the pulley system. Okay. Right. Now, remember, we had a problem to solve. Right. Write a design brief. What is our problem? We are given a task of designing and making a winch that can lift 3 times the size of a normal vehicle. So we need to make a winch for a tow truck. Right, so you know that when we have a problem, we have to write a design brief of how we are going to solve it. Write a few short, clear sentences that summarize the problem that needs to be solved, as well as the purpose for the proposed solution. Begin your first sentence with the words, I'm going to design a gear system for the winch of a tow truck to allow it to pull a vehicle that is up to 3 times as heavy as an ordinary car. That is our design brief. That is what you should be working on. So everything that you'll be investigating, everything that you'll be studying must be relevant to this. We must understand gears. We must understand mechanical advantage. We must understand winches. We must understand a relationship between the winches and the pulleys. All right, let's go. Right, specifications. Now, which stage of the design process is this? Which stage of the design process is this? Where you have to deal with specifications for your solution. Come grade 8. Can you name, let's start by naming the stages of the design process. What are they? Come, my children. We have Daniel today. Daniel, don't you want to speak to me? Yes, let's investigate, design, make, evaluate, the last one, Chedza, communicate. Thank you, my boy. Thank you, thank you, thank you. Yes, IDMEC, investigate, design, make, evaluate, and now, tell me, which stage is it that we have to deal with specifications? Oh, my girl, I'm sorry. Chetza, am I pronouncing your name correctly? Oh, thank you. At least I've got 1 out of 2. All right. Now, which stage is it where we have to write down the specifications? It's the design. Thank you, Daniel. Now, I want you to imagine that we are dealing with a client. The client is the owner of the tow truck. And we, technology students, are the company that is going to solve this problem for the client. Okay, now, it is the client who normally comes up with the specifications, or we can negotiate the specifications with the client to say, oh, you have such a problem, or this is what I must design and make for you. All right, let us talk. How do you want this thing to be? Okay, and then the client can start giving the specifications, or we can add, because we are specialists, okay? We can add to the specifications to say, look, for your winch to have such mechanical advantage, we must also add this so that the client is not surprised when we come up with a product that has some features that he didn't expect to see. So the specifications are a communication between the client and the technologist, okay? And they are giving the details of what the solution should look like. Right. Now write a list of specifications for the new winch solution. Remember, specifications are lists of things that your solution must do and some things that it must not do. See? Right. The winch must be able to pull vehicles that are up to 3 times as heavy as an ordinary car. The gear system should not change the direction of rotation, obviously, because the tow truck must hold, okay? And the car that is being towed, it must be attached to the system. It is not the weight that must pull the tow truck. It is the tow truck that must pull the weight. Okay? The cable of the winch must be strong enough to not to break when it pulls the weight of 3 cars. Right. The design of the improved winch. Remember, this tow truck does have a winch. We just have to design a better one. Describe how you are going to improve this winch. I'm going to add a gear system to the winch that gives a mechanical advantage, but that does not change the direction of a rotation. Remember, we saw, let's go back. We saw this winch, and this winch doesn't have a gear system. You see, so it is lifting a maximum weight of 2,000 kilograms. Okay, right. This winch has a potential of lifting 10,000 kilograms if a gear system could be attached here. But this is a different winch. It's not the winch of a tow truck. It is the winch of a mine head gear. Okay. Now, how will you know that the winch can pull vehicles that are up to 3 times heavier than an ordinary car? Okay, how will you know? When you are designing this, how will you know that now this system can give me a mechanical advantage that is able to pull the weight of 3 cars? The driven gear will be 3 times the size of the driver gear. I think you understand now. Okay, do you all understand what the system should be like? Remember when I showed you the system of that other winch, I showed you that the small gear is the driver, and its input force is multiplied in the output force, in the output area of the bigger gear. So that is what is going to happen here. Now, because now we know, we start making freehand sketches, okay? And we start drawing. So I took this from your workbooks, but I want us to look at it, okay? This is a square grid, as I said yesterday, and this is the motor. You saw the motor, ne? Now you have to attach a gear system to the motor. And we are not worried about the drawing of the motor. That is why it is given to us already. But because we have been, in the past 2 days, we've been doing 2-dimensional drawings of gears. You are going to attach that 2-dimensional drawing of a gear system to this motor, okay? That will not be such a problem because you have done that already. Now let us investigate winches. Right. This is another gear system of a wind turbine. Where can you get a wind turbine? Can you think of a place where you can get wind turbine? In a fan, good. In a car, yes. In the fan of the car has a fan in the engine there's a fan. Okay. In a windmill, in an office fan, yes, a desktop fan, yes, Nhlanhla. What about a wind-operated power station? Okay. You get wind turbines, many wind turbines in a wind-operated power station. I know that you saw a coal-powered power station, okay? Now, when you look at this system, all right, you have a gear system here, and there is a small gear and a bigger gear. The axles are not the same either, okay? And you have this drum here, okay? Now, when you look at this system will give us mechanical advantage if this small gear is the driver. If it is driving this bigger gear, then that will give us mechanical advantage. Look at the system shown below. It shows the inside of a wind turbine, right? You find this in a wind-powered power station. The wind turns the propeller. The wind turns the propeller, and the propeller turns an electric generator to make electricity. Okay, this is for the power station. But now let us look. If the input is on the side, the wind will make the blades of this turbine to spin. So the driver is the bigger gear and the driven is the smaller gear. What is the output? What is the output here in this system? Obviously, the input is on the blades. What is the output? No, not mechanical advantage this time. I said when we speed advantage, that's good. I said when I started, if this small gear was the driver, then the output would be mechanical advantage. But now looking at this system and looking at where the input is, the input starts here on the blades. The wind turns the blades. So if the wind turns the blades, it will make a rotation on the bigger gear. So the bigger gear in this case is the driver. And then the driver will then turn this smaller gear. And then that will give us speed. And that will be transferred to the generator, okay? The generator will then create electricity, okay? So you see the difference now between the mechanical advantage of the winch and the speed advantage of the propeller. In the propeller, we need speed advantage because we want speed advantage, okay? Because we want a quick movement that is going to get into the generator so that the generator can turn the energy into electric energy. So this system gives us speed advantage, right? Now, when you look at this, what is the problem? The problem with wind turbines, the blades of wind turbines turn slowly, about 9 to 19 revolutions per minute. That is very slowly. Now they depend maybe on the speed of the wind or the strength of the wind. But the electric generator that is driven by a wind turbine needs to run faster. A turbine manufacturer needs a gear system that will make the generator turn at least 4 times faster than the wind turbine. What must we do here? How can we solve this problem? Because we can see that the blades are being turned by wind, and we only get an output of 9 to 19 revolutions per minute. Now, we want this turbine to turn faster. What do we need? What is it that we need to do in order to get speed advantage? We want speed advantage here. This is what we are going to do. All right. I'm going to design a gear system for a wind turbine. This gear system will convert the slow rotational speed of the rotors into a rotational speed of a generator that is 4 times faster. Okay? Specifications for this solution is that the driven gear must turn 4 times the speed of the driver gear. So the size of the gears will inform that. Okay, so it means that the driven gear must be 4 times smaller than the driver gear. So you will get an output of a speed that is 4 times faster. Okay, I'm just trying to make you see the systems that you need for mechanical advantage and the systems that you need for speed advantage. Okay, if you want bigger mechanical advantage, the driver gear must be, remember for the winch of the car, we wanted a mechanical advantage that can take the load of a car that weighs 3 times more than a normal car. So we need to make the driver gear a gear that is 3 times smaller than the driven gear because we want mechanical advantage. In this case, in the wind turbine, we want a speed advantage system that is 4 times faster. So we are going to make the driver gear 4 times bigger than the driven gear so that we have a speed advantage that is 4 times bigger. Okay? Right. I hope you understood that. Mechanical advantage and speed advantage. So let us look at the drawings of gears. Tell me, what type of a grid is this? Is it an oblique grid, a square grid, or an isometric grid? What do you call this? Is it an isometric grid or a square grid? I've shown you a square grid and I said you draw oblique drawings on the square grid or you draw 2-dimensional drawings there. Okay? This is an isometric grid. Remember when I showed you? Yes, isometric grid. Very good, my children. Now, the isometric grid has a vertical line, okay? A vertical line and slanting lines, okay? These lines have already made our lives easier because if these lines were not here, we would use set squares. So what is the angle of the slanting lines in relation to the vertical line? And you have a horizontal line that runs across these squares, okay? What is the angle of these slanting lines? The angle is, okay, let me ask you. We have a 45-degree set square that we use to draw our oblique drawings. And we have a 30-degree set square that we use to draw our isometric drawings. So these lines that are slanting are already drawn at an angle of 30 degrees in relation to this vertical line and an imaginary horizontal line here. So you can draw on this, you can draw freehand on this, or you can use your ruler, but the angle is already done for you. Now, we are going to draw our gears step by step, okay, on this isometric grid. So remember, in a different video, I showed you how to do your drawings and to make a round hole on an isometric drawing. You see, on an isometric drawing, the round shape, it doesn't take a round shape as you see it in two-dimensional drawings. It becomes more of an oval shape. So that is what we are going to draw now. We want to draw a gear. So I'm going to show you the steps. You start by making this square. Okay, you are making this. This should be a square, although it is skewed in isometric drawings. It should be skewed. Right. So you just follow the line of the squares and you make that. You are planning your drawing. And then you make construction lines this way, right? And you have this other construction line. And that's supposed to be your construction lines for the circle, right? The next step, you start by locating the point, the center point. This is your center, right? And then you draw this construction line, although it's a broken chain line here. And then you draw another broken chain line vertically like that, right? So it's more like your face, your square face, just facing to the left. It does look like it's facing to the left, doesn't it? All right. And then the next step, step 5, you plot your dots there in the centers of each line of the square. Okay? You plot your dots there, your markers, you plot your markers there. This should be the center of this line. And this should be the center of this line because you know it's 2 squares just in the middle of those 2 squares. And even here, the same, and there. Then after that, you draw a line, a curved line from dot to dot. Okay? And then there you have your solid line. And then because it's 3-dimensional drawing, you add another dimension to your gear there. You've added it. You are making your circle now. You're making it 3D. And then you can add a shaft. When you add the shaft, you follow this line. You follow this line. You add the shaft along this line. This is the shaft for your gear, okay, or the axle of your gear. You add it there, right? Okay, that's your gear. Okay, and then you can add here, practice, you do this other gear, this bigger gear. The way you drew this small gear is the same way you're going to draw this big gear. You have your vertical broken chain line there, and then a slanting broken chain line, and then you count the number of, if this one is, this one is 3 times bigger, we are drawing a gear system for the winch. This one is 20 millimeters, so this one is 60 millimeters. So you are going to draw it in the same way that you drew this one. You take these steps, just that because this one is 20 and then this one is 60, you are going to make it 3 times bigger for the bigger one. You are going to make, you are going to count how many squares. We counted 2 here. If it's 3 times bigger, so how many squares are we going to count? We are going to count 6 because this one should be 3 times bigger. So on each side on the grid, you are going to count, the line is going to stretch over 6 squares, 6 squares downwards, 6 squares this way, and 6 squares that way. Okay? And just this time, you're going to have a gear mesh. So your outer diameters are going to connect. The outer diameter of this one will connect to the outer diameter of this one. So that is how you are going to draw your gears. And this is how you draw your gears 3-dimensional. You have a 3D drawing. If you are ever asked to do a 3D drawing of your gears, you do it this way. Okay? Right. Now let us look at bevel gears, bicycles, and systems diagrams. These are other gears, but gears that are attached to a chain. So we call this a chain and sprocket system. Okay, it's a photograph of the chain drive of a bicycle taken from your Sasol Inzalo workbook. Okay, now, chain drives, how do they operate? When you ride a bicycle, you pedal. The pedals push the cranks up and down. Okay, the pedal actually is a crank system. It's part of a crank system. The cranks force the chain wheel to turn. Attached to the chain wheel is the chain. When a cyclist pedals, the chain is pulled around in a clockwise direction. This way, clockwise. The chain meshes with the gears on the cogs. The cogs are the teeth of the gear. And on the chain here, you have a space that is compatible with the size of the gear, right? The gears make the back wheel turn and the bike move forward. So the motion here, the rotary motion of this gear, it's a spur gear, and it is attached to the chain. When it does that clockwise rotary motion, that rotary motion is converted into a linear motion. Okay? So there is your driver gear and there is your driven gear. Okay, right. But remember, when we did this, we have done this before, it becomes very important to look at the number of teeth of these gears in the chain and sprocket system of the bicycle. Okay? You use different combination of gears on a bicycle when you cycle up a moderate slope or a steep slope. Okay? So you actually need more, you need torque. You need torque for an uphill drive because you need more power, okay? It's not like on a moderate incline. Okay, right. Now, let us look at the systems diagram of a bicycle. Because it is a system, all systems in mechanical systems and control, they must have a systems diagram. You must be able to analyze the input, the process, and the output. A systems diagram shows how a system will change inputs into outputs. The process changes the inputs into outputs. Okay, so actually the machine is right here. The processing is right here. When you change the pedaling force or the pedaling speed on a bicycle, the output speed will change. The systems diagram will help you to work out how this will change. Input is the pedaling force. When you put your foot on the pedal and then the crank starts to turn the gear clockwise. The process is how the movement of the gear, the force is transferred from the gear to the chain. And then you get circular movement converted into linear movement. The output is speed or force. So for this, you need force. Do you have high speed on a steep incline? Do you have high output force or high speed? Here. Grade 8. On a steep incline, do you have high output force or do you have high output speed? On a steep incline. Natalie, you're right. You have, on a steep incline, you have high output force. And that is what we call torque. So, yes, you need force, okay? You need force for this, okay? Right. So, the output is speed or force, but you must be able to analyze the speed because it will differ on a downward slope or an uphill slope. Okay, right. Now, you can use systems diagram to represent gear systems instead of drawing them. Okay, right. This illustration, it has a speed advantage of 3:1. You can use the diagram to work out what the output speed will be if the input speed should change. If the input speed of the car's engine on the driver is 500 revolutions per minute, then the alternator speed will be 1,500. That's a mechanical advantage of 1:3. Okay, it is multiplied by 3 in the alternator. Okay, so this should be like the alternator of your car. Okay, this a bicycle chain drive, that is what will multiply the input force, right? And then you have a rotational speed of the driven gear. Okay, tomorrow we'll look at the bevel gears. We have been sketching spur gears. We sketched them 2-dimensional and we sketched them 3-dimensional. And then we looked at the spur gears in the gear system of a winch. We saw the spur gears and also in the wind turbine. And then we look at bevel gears tomorrow. Thank you, grade 8. Have a lovely day and all the best with your assessment. Don't be frightened, it's not difficult.